In kinetic molecular theory, we're really going to zoom in to the micro scale and think through what's happening with a gas. Now, this has a lot of mathematics sitting behind it, and we're not going to focus in on the mathematics, much like when we talk about quantum mechanics at the Chemistry 1 level. To do that, we'd have to think about statistics at the same time as some differential equations and have things evolve in multiple dimensions, because we're going to be talking about a 2 or 3-dimensional space and adding time into that as well. Now, rather than going that far, we're going to focus on the conceptual things that come out of it. Now, let's think about an ideal gas for a moment. An ideal gas has lots of space between our molecules, and we've declared that molecules are not going to interact except by colliding. There's no repulsions, there's no attractions. They're just bouncing off each other whenever they hit. The energy is being conserved. These are the basic ideas that we have as part of our ideal gas law. Now, let's take a look at some implications that came from that and how it led to kinetic molecular theory. So, one thing we've pointed out is that the volume of our packed particles is going to be very small versus the volume of the gas. In other words, if I take a small piece of dry ice and then I allow that gas to sublimate and turn into a gas and expand, that gas is going to take up a lot of space compared to when it was compacted into a solid. And we can't really have a solid compact down much more than its normal spacing, at least not without some extreme conditions. And when I say extreme, I mean things like neutron star extreme. We're talking about just things normally happening on a planet, and we're going to have things that are liquids and solids typically not be more compressed than they are on Earth. Now, we're also going to insist that our particles are only moving in random straight lines, except when they collide. And when they collide, they bounce off in a new random direction following a straight line. There's no curves because there's no attractions or repulsions turned on. We've turned all those off for our basic ideas here. And that's going to be reasonably true because of how strong the force is as it propagates out from a molecule or from an atom. That attraction or repulsion drops off very quickly with distance, to the point where once you get a little bit away, my joking "I can't see you" rule applies pretty well. So that's what we're going to be talking about with ideal gases. Now, all of our collisions are going to be elastic, and that means that no kinetic energy is lost. You can change the ratio between the two atoms when they collide. If this were a perfectly stationary atom, under kinetic molecular theory and our ideal gas law, this molecule comes in and collides with it. The total amount of energy that this has in its kinetic energy when it hits is now the amount that I've got to space between these two. So both these are going to ricochet off at a slower speed. It's going to be much like when you're playing pool and you hit the cue ball and you hit the balls to break them. The cue ball is moving fast, everything else is stationary. That momentum has been transferred to the others, they bounce off elastically, and everything starts moving with that total kinetic energy. That's more or less what we're talking about for kinetic molecular theory.